Hey everybody, welcome back to Chem 104. We are starting chapter 11. We don't do the full chapter. We're just going to pull out some bits and pieces from chapter 11 that will complement chapter 9, which we just covered. So we're starting with section 11.4. A little bit of a strange place to start, I know. But again, we're not covering the entire chapter, just a few sections within the chapter. We're going to talk about dissociation of weak acids and bases. So in chapter 9, we talked about strong and weak electrolytes and non-electrolytes. This week, we're focusing on acids and bases, which can fall into those categories of strong or weak electrolytes. So first, we're going to learn how to write the expressions for dissociation of a weak acid or a weak base. So when you see dissociation of a weak acid, what you should be thinking in the back of your mind is a weak electrolyte. Everything that applies to a weak electrolyte that we talked about in chapter 9 applies to a weak acid. So strong acids we talked about in chapter 9 as well. Those fully dissociate, those are like strong electrolytes. What we're focusing on is the weak ones. And the weak acids, there's an equilibrium process when they dissociate. They partially dissociate in water. They reach an equilibrium with undissociated weak acid molecules, okay? So what that means, if we look at the equation below, is that we have an acid here, which is a weak acid, and it's in water, and it will dissociate to form what's called the hydronium ion, which is sometimes written as just H+. And then we also form what's called a conjugate base. And we're going to cover what that means a little bit later on. But these are the ions that are formed. The undissociated weak acid is here. And the ions that it forms are on the product side. And there's an equilibrium which is shown with these two arrows. What we're interested in when we're writing dissociation expressions is the concentration of the products and the reactants. We're looking at the molar concentrations. We talked about molarity in chapter 9. So that's moles over liters, right? We care about the molar concentration of products and reactants. But what we don't care about is pure liquids that have a constant concentration. What that means is when we're writing our dissociation expressions, we're not going to include water. We omit that from our expression. When we're writing a dissociation expression for an acid, it's called an acid dissociation constant. And we use Ka for that. So this is the same weak acid dissociation that I showed on the last slide. We've got formic acid, which is our weak acid, and we have water. That water is not going to show up in our dissociation expression. Remember that on the left-hand side, we have reactants, and this is for any chemical equation. And on the right side, there are products. When we write our Ka, that acid dissociation constant, we want the concentration of the products on the top divided by the concentration of the reactants. What that looks like in this specific example with formic acid is we have the products of hydronium, H3O+, and we have the conjugate base that's formed. Those are our products. You write those in brackets, and what that means is the concentration, the molarity of each of those compounds. They're ions. On the bottom, we're going to write all the reactants that are not pure liquids. So remember that red X on the water? We don't care about it, so we're not going to write that there. All we're going to write in the denominator is the formic acid, which is our weak acid. Whenever you're writing a Ka, this is the form that it's going to take. The ions that are formed as products are on the top. And then you have the concentration of the acid on the bottom. Never include water. Never include it. We do not want to see it there. Now, there's some things that we can predict based on how big or small the Ka value is. So I'm going to rewrite the equation that we just had before. We're going to keep using it as our example. There's formic acid. And some water. There's our equilibrium. We form hydronium and conjugate base. Reactants are on the left. Products are on the right. And I'll remind you of what our Ka expression is. We took the ions from the product side. We want those concentrations on the top. And the concentration of acid on the bottom. Now this Ka actually has a value. It's equal to something. For formic acid, it's equal to 1.8 times 10 to the minus 4. There are no units for the Ka value. In general, when the value of Ka is small, the equilibrium lies to the left, favoring the formation of the reactants. What that means is you're going to have more undissociated weak acid. So in our example, what that would mean is we'd have more formic acid. And our Ka of 1.8 times 10 to the minus 4 is fairly small. When you have a large Ka value, the equilibrium lies to the right, favoring the products. That means that you're going to have more ions. What that means is hydronium and conjugate base. Weak acids have small Ka values. We said that formic acid is a weak acid, so it's small. 1.8 times 10 to the minus 4, that's a pretty small number. Strong acids, ones that are considered to be strong electrolytes, they have large Kas. So they're going to have more ions, and they're going to pretty much completely dissociate. You'll need to remember the relationship between Ka and whether or not the equilibrium lies to the left or the right, and what that means. Now there's a Ka, there's also a Kb, because we can talk about bases, and bases can be weak or strong. The dissociation constant, the same rules apply. When you have a small Kb, the equilibrium lies to the left, and that favors the reactants, which means undissociated base. When Kb is large, you're going to favor the products. The products are hydroxide and conjugate acid. And again, we'll talk about what conjugate base and conjugate acid means in just a little bit, so don't worry. Hydroxide, I'm going to highlight it. I'm going to highlight the word and the ion. This is the hydroxide ion. So the same rules apply for Ka and Kb. Small Ka, small Kb, that means that you have a weak acid or a weak base. If it's large, then you've got a strong acid or strong base. We write the Kb exactly like we write the Ka expressions, where the products are on top and the reactants are on the bottom, and we don't include water. This table, 11.4, has values for Kas and Kbs for select weak acids and weak bases. You may need to reference this for your homework. You won't have to memorize any of these. It will always be provided if you need to know the Ka. .5 is a great table that summarizes the characteristics of acids and bases. We talked about these, but if you need something to look at that kind of brings it all together, this is a great table to put in your notebook, and one that you can use to kind of fill in the blanks and make sure that you understand the concepts. So you can keep all the characteristics for Ka and Kb, and then fill them in for strong acid versus a weak acid as a way to test yourself. So let's do a little practice. We need to write the acid dissociation expression for nitrous acid. Nitrous acid is a weak acid. It does not fully dissociate. That's our acid. It's aqueous, that means dissolved in water. And some of that water is going to react with the acid. We have our equilibrium arrows, one going in either direction. Acids always form hydronium and a conjugate base. So let's write some of these things down. When you're writing the dissociation expression for an acid, you have the acid plus water, the equilibrium, the hydronium ion, plus what you're essentially writing is your acid minus one hydrogen. So it's the chemical formula for the acid minus hydrogen. Now, if I were to ask you, is the Ka for this going to be big or small based on the fact that this is a weak acid? Think about that answer for a second. Do you expect the Ka to be big or small? While you're thinking about that, we're going to write out the expression, because what we just did was write out the equation, right? This is a chemical equation, but we need the acid dissociation expression, which comes from the equation. We put our products on the top. And on the bottom, we only put the acid because we don't care about the water. Okay, so the Ka for this, since it's a weak acid, will be small. That wasn't a part of the question, but I just wanted you to think about it, because you'll need to do that for your homework and for the exam to make those relationships. We talked about acids and bases dissociating, but you'll notice that we were talking about hydronium and hydroxide. Where did those come from? They come from the dissociation of water. Water will produce hydronium and hydroxide in small concentrations, and it'll be in equilibrium. So we're going to learn how to write the water dissociation expression and how to do some calculations with those ion concentrations. Water is awesome. If you haven't figured that out by now, it is an amazing substance. Pretty much a universal solvent, important for all life on our planet. Water is what's called amphoteric. It can act as an acid or a base. So add that to your list of things that water can do. Water's polar. It's amazing. Okay, it's an amazing little molecule. Very, very important. The hydrogen, the ion, is transferred from one water molecule to another. And that's how it forms the hydronium and the hydroxide. So one water molecule acts as an acid, the other one acts as a base. And what does that really mean? An acid is a hydrogen donor. So it will give up one of its hydrogens. A base will accept that hydrogen. So if we have one of our water molecules saying, hey, you know what? Someone can have this hydrogen here. And the base says, sure, I'll take it. So it adds on, and you form a conjugate acid and a conjugate base. So what was the acid it loses a hydrogen and becomes the conjugate base. What was the base gains a hydrogen and becomes the conjugate acid. So there are what's called conjugate acid-base pairs. What I find helpful is to track the hydrogen. So if you have a highlighter or a marker, or you can circle the hydrogen on the acid and then figure out where you have an extra hydrogen on the product side that you didn't have it before on that molecule. So track the hydrogen. That way you can know, okay, the hydrogen went here. Then you can form your conjugate acid-base pairs. There's an equilibrium that's reached between the conjugate acid-base pairs with water. And because of that, we can write the water dissociation constant, which is Kw. There's a forward and reverse reaction. Forward reaction, we're making hydronium and hydroxide. And in the reverse reaction, we're just making more water, right? We said that when we write these dissociation expressions, that we don't care about the pure liquids. Pure liquids don't have a changing concentration. That means that for our expression, the Kw is simply equal to the concentration of hydronium times the concentration of hydroxide. And at 25 degrees Celsius, that is equal to 1 times 10 to the minus 14. And again, these dissociation constants do not have units. So the product of these ions is equal to 1 times 10 to the minus 14. We don't have any concentration units or anything like that. What we can do is talk about whether or not a solution is acidic, basic, or neutral based on the concentration, the relative concentrations of hydronium and hydroxide. If they're equal, then the solution is neutral. Pure water, equal concentrations of hydronium and hydroxide. That's pure water. Okay. If, however, hydronium is greater, then your solution is acidic. If hydroxide is greater, your solution is basic. So these are the first definitions that we have of neutral, acidic, and basic. We'll be adding on to that. There's different ways that we can describe neutral, acidic, and basic solutions. This is just one of them. We can use the Kw to calculate the concentration of hydronium or hydroxide in a solution. If we know one, then we can use the Kw to calculate the other. So if we know Kw is equal to hydronium times hydroxide, then you can divide by hydronium, and then you end up solving for the hydroxide concentration. You can do the same thing, and I'm going to quickly rewrite it here. You can do the same thing to solve for the hydronium. You just divide by OH, that hydroxide, on both sides. And that gets you to this equation. Hydronium is equal to Kw over hydroxide. So in pure water, we said that hydronium and hydroxide are equal. That means the concentration for both of those is 1 times 10 to the minus 7. That's a neutral solution. If you add acid to pure water, you're going to increase the hydronium concentration. That's what these bars are showing. You can see the up arrow here. We've increased the hydronium concentration above 1 times 10 to the minus 7. So now our solution is acidic. When you increase the hydronium concentration, you also decrease the hydroxide. The opposite is true for a basic solution. If you add base to water, you're going to increase the hydroxide, the hydroxide. All these high words, the hydroxide, hydronium. It's a little bit of a mystery sometimes. You got to keep those words straight. So we increase the hydroxide when we add base to pure water. And we decrease the hydronium. That is a basic solution. And this chart just shows you a comparison of acidic, neutral, and basic solutions. So if you're a visual person and the bars help you, this would be a good thing to recreate in your notebook so you can see the difference, and it'll help you to identify an acid versus a base versus a neutral solution. This table here, 11.6, gives you some examples of types of solution, neutral, acidic, basic, and the concentrations of hydronium and hydroxide ions. Let's do some practice. I encourage you to pause it here and give it a shot, and then you can turn the video back on and see how you did. What is the hydronium concentration of a solution if hydroxide is 5 times 10 to the minus 8 molar? Whenever you see hydronium and hydroxide, think Kw. What we're solving for is a hydronium concentration. We need to isolate that on one side. So now we have hydronium is equal to Kw over the hydroxide concentration. And remember, the Kw is equal to 1.0 times 10 to the minus 14 at 25 degrees Celsius. So just assume that that's the Kw value that you're going to use. Unless you're told otherwise, assume that value. Now what we do is substitute in the numbers that we have. The Kw is 1.0 times 10 to the minus 14. OH minus, that concentration was given to us in the problem. Hopefully you can see where that comes from, because sometimes it's a little bit difficult to keep track of where information and all these numbers are coming from. So I'll try to highlight or underline with matching colors so you can see where I pulled the information from. When you put this into your calculator, you need to make sure that you refresh your brain on how to use exponents with your calculator. So make sure you know how to do that. For some, it may be helpful to use parentheses around each of these numbers in scientific notation, just to make sure that the calculator does the correct order of operations. When you do the division, you should get 2.0 times 10 to the minus 7 molar. Bonus question: is this an acidic solution, basic solution, or neutral? A neutral solution, both of these would have a concentration of 1.0 times 10 to the minus 7. We've noticed an increase in the hydronium concentration and a decrease in hydroxide. So that means this is an acidic solution. That was not part of the question, but I always try to add in a little bit more practice. Get you thinking and try to link together the concepts in the chapter. Now we're going to jump to 11.6 and talk about the pH scale. Since we're talking about acids and bases, we have to talk about the pH scale because it describes the acidity of solutions. You may have seen in a chemistry lab, if you've ever done high school chemistry, testing the acidity of a solution, a little dipstick that you dip it into a liquid for a couple of seconds, and then the colors change, and you match those colors to the colors on the box to estimate the pH. The pH of a solution indicates how acidic something is. So it ranges from very acidic to very basic. The values usually range from 0 to 14. When you have a pH less than 7, you're acidic. 7 is neutral. Greater than 7 is basic. And that's what this table says. So we now have two definitions of what it means to be acidic, neutral, and basic. pH, and we can also talk about the change in hydronium concentration. So I would suggest putting that into your notebook, and we're going to talk about one more way where we can identify acidic, neutral, and basic. So leave some space. Like I said, the pH of a solution can be determined using a dipstick, pH paper, okay? That's what letter B is. In A, there's a pH meter. So you can take that probe and stick it down into your solution, and based on the temperature, and it uses pretty much electricity to figure out how, the concentration of hydronium ions in solution. There's some math going on in there, and it'll tell you the pH. In C, you can use different indicators that will turn colors that correspond to different pH values. So there's certain chemistry that happens with a chemical. There's a lot of different indicators. And once a certain pH is reached, then that chemistry happens and you see a color. So it's very pretty, very happy. This image just shows you the pH of some common substances that you might have around the house or that you may have encountered in life. So 1 molar HCl, that's hydrochloric acid, very, very acidic. Close to that, gastric juices, so that's in your stomach. Okay. Lemon juice, very acidic. Something that you may be surprised by is that carbonated beverages, so your favorite soda, very, very acidic, can do some real damage to your teeth. Coffee is also acidic. Our drinking water is slightly basic. So is blood plasma, and we're going to talk about blood plasma towards the end as a chemistry link to health. Seawater, more acidic, more basic. Ammonia, which is a cleaning agent, and bleach, those are very basic. And then sodium hydroxide, which you may also see as lye, that is super duper basic. So you don't want to get that stuff on your skin. Any strong acid or strong base, you don't want it on your skin, don't want it in your eyes, you certainly don't want to ingest it. So be very careful. The pH scale itself is a logarithmic scale that corresponds to the concentration of hydronium in aqueous solutions. So it's the negative log base 10 of the concentration. This is the equation. This is what it looks like. Now, if you're looking for the log function on your calculator, if you have a TI-89, you're going to have to go to the catalog. There's a little button that says catalog on it. And then you have to search for this. Log with the parentheses after it is log base 10. You can have different bases, log base 2, log base 10, those are the two common ones. So you'll have to, if you have a TI-89 calculator, you'll have to go to the catalog and then search for this function. I'm not sure on other calculators if you have a log button or if you have to search for it. But if you don't see one on your scientific calculator, that means you have to search through a menu of functions. So make sure that you know how to use the log function. pH is already a little bit weird because we're using a log, but it's also a little bit strange in terms of how you determine significant figures. So the number of decimal places in the pH value is the same as the number of sig figs in the coefficient of the hydronium concentration. So what does that mean? We have a concentration of 1.0 times 10 to the minus 2 molar. That's our hydronium concentration. This 1.0, this tells us the number of sig figs in the concentration that we have. That's what the coefficient does in scientific notation, right? So we've got 2 sig figs here. What that translates to is we need to have 2 decimal places to have 2 sig figs. So that 2 that comes before the decimal place, that's not included in the sig figs. What we care about is how many decimal places after. So that you may have to practice a little bit because we're so used to matching up the number of sig figs, let's say, when we're doing multiplication, but that's not how we do it for pH. When you change one pH unit one way or the other, it's not just a change of 1, it's a change of 10. It's a 10-fold change. So when you go from a pH of 2 to a pH of 3, what we're looking at is a concentration of hydronium of 1.0 times 10 to the minus 2 versus 1.0 times 10 to the minus 3. That's a big difference. As the pH decreases, the concentration of hydronium increases. I like to write things like that with arrows because the arrows tell me what direction we're talking about. So if we decrease the pH, we increase the concentration of hydronium. So that's how these are related. Let's do a pH calculation. I encourage you to pause it here, read through the problem, give it a shot, and at the very least, if you don't want to try the problem like solving it on your own, I highly recommend that you try out the log function on your calculator to make sure that you get the same calculator answer as I do. Make sure that you know how to use that log function because on your exam or even with the homework, you don't want to lose points just because you don't know how to put it into your calculator. And for the exam, you're not going to have access to the internet to just say, okay, negative log, blah, blah, blah. Google what's the answer. So learn how to use your calculator. So aspirin, which I'm sure you're very aware of what that is, it's acetylsalicylic acid. That's the chemical name. And it was the first non-steroidal anti-inflammatory drug, which you may see abbreviated as this, used to alleviate pain and fever. If a solution of aspirin has a hydronium concentration of 1.7 times 10 to the minus 3rd molar, what is the pH of the solution? So you see that whole entire paragraph? Really the only thing that's relevant is that concentration and this piece of the question, what is the pH? So don't be intimidated by large word problems. Oftentimes you can boil it down to a couple of pieces of information that are relevant. Since we have to calculate pH, it's a good place to start by writing down what the equation is for calculating the pH. So pH is equal to the negative log of the hydronium concentration. Don't forget this negative sign. It's very small, very easy to overlook, but you will get a very wrong answer if you do not include the negative sign. All we have to do is take our hydronium concentration and substitute it in where we see hydronium concentration in the equation. You enter this into your calculator. Again, don't forget the negative sign. It is key. If you don't include it, you will get a very wrong answer. I'm going to circle it here. Don't forget the negative sign. Your calculator will tell you this answer. So you should at least try putting this into your calculator and see if that's what you get. But we need to deal with significant figures. In our concentration, 1.7, that has 2 sig figs. What that means for our pH is that we need to have 2 decimal places for our sig figs. So the pH is equal to 2.77. Since we know how to calculate the pH from the hydronium concentration, we can also reverse the calculation to get the concentration of hydronium. For a whole number pH value, the negative pH value is the power of 10 in the hydronium concentration. What does that mean? So let's say that I had 1.0 times 10 to the minus 7 molar as my hydronium concentration. The pH is going to be equal to 10 to the minus, or the hydronium concentration is going to be equal to 10 to the minus pH. If we know that the pH is going to be 7, because it's a neutral, right? We fill in that 7. This is a neutral solution where we know the pH is equal to 7. Our hydronium concentration we know is 1.0 times 10 to the minus 7. If our pH is 7, you put it in right there at the top. I'll highlight it. But if you don't have a whole number, which is very possible, then you're going to have to use the 10x key. You'll need to find that on your calculator. It is usually a second function key, so it's not like a plus or a minus, something that you see the plus, you hit it, bam. But you may have to hit a button that looks like this first. That's the second function key. So again, make sure that you know how to use your calculator. Let's do a practice. And again, I encourage you to pause it here and try it. But if you don't, at the very least, make sure you know how to use your calculator to get to the right answer. Determine the hydronium concentration for a solution that has a pH of 3.42. We know this equation for finding the hydronium concentration with pH. So all we have to do is substitute in our pH from the problem here. Again, there's a negative sign in front of that pH. Don't forget to put that in. Otherwise, you will get a very strange and very wrong answer. These concentrations should be small. 10 to the negative something. Small. So if you get something big, if you get 52, you know you did wrong somewhere. So please, please, please make sure that you know how to use your calculator correctly. We also need to consider significant figures. This pH has 2 places after the decimal. That means that our hydronium concentration needs 2 sig figs. So when you put this into your calculator, you should have 2 sig figs and this should be what you get, 3.8 times 10 to the minus 4, and the units here for the concentration is molar. So when we're talking about hydronium or hydroxide concentration, molar. Now let's think about this in the context of whether or not it's acidic, basic, or neutral. The pH is 3.42. The pH is definitely less than 7, which means that it is acidic. But we can double check our work to make sure we got something that's reasonable. 3.8 times 10 to the minus 4 molar. Well, we know that for something acidic, that we should also have a hydronium concentration that's less than 1.0 times 10 to the, not less than, greater than. I'm thinking about the pH still. The hydronium concentration should be greater than 1.0 times 10 to the minus 7 molar because it's acidic. So we increase the hydronium and decrease the hydroxide. Okay. So that's the way that you can check your work and make sure that your answer makes sense. Moving right along to buffers. Buffers are related to pH and acids and bases because you use weak acids and weak bases to create buffer solutions. A buffer solution maintains a pH. It can neutralize small amounts of added acid or base. If you took water, just plain water, and you add acid or a base, you're going to have a really big change in pH. And that's what we have in the top here. We'll call this part A. We've got plain water, and if you add acid, you're going to get a low pH. You add base, you get a high pH. With a buffer, you can add a little acid or a little bit of base, and you'll still have about the same pH. So if you're starting with a pH of 7, you add some acid, 6.9. That's not really a change. You add a little bit of base, 7.1. Not really a change from a pH of 7. That's what a buffer solution does. It maintains the pH. In the body, buffers absorb hydronium and hydroxide from food that we eat and from the cellular processes that are going on to keep us healthy and alive to maintain proper pH. So we absolutely require a certain pH of our blood and all of our bodily fluids. and it's really important to the proper function of our cells and the blood. The blood has a pH of about 7.4. And if you change the pH of blood, you would actually affect how your body takes up oxygen and a lot of other cellular processes, because the pH can affect the structures of proteins and it affects the way that chemistry is done. So what's in a buffered solution? You have a combination of an acid-base conjugate pair. So we talked about that a few sections ago. You need a weak acid and a salt of its conjugate base. What does that mean? I'll identify it for you. The weak acid, here's a weak acid. This is acetic acid. If you take off the hydrogen, you get the conjugate base, the acetate ion. In a buffered solution, you'll likely have equal concentrations of a weak acid and its salt. An example of the salt of a conjugate base would be, let's say, sodium acetate. Salt is just a fancy word for saying an ionic compound. So let's say that we have this buffer with acetic acid and sodium acetate. When you dissolve that salt, you're going to make acetate ions and sodium ions. What we really care about is the acetate ions. That's going to boost the amount of conjugate base over and above what the weak acid would produce alone. Remember that with the weak acid, you're not really forming a whole lot in the way of ions. That's why it's a weak acid. It doesn't dissociate fully. So what you have is a large amount of your weak acid, and you bolster the amount of the acetate ion, which is the conjugate base. And that's from the salt. If you add a small amount of base to this buffer, you're going to neutralize that with the acetic acid. That's going to shift the equilibrium towards the right. That means you're going to make more of your products. This is our added base. And we're going to increase our product. Now, we're not concerned about the water, remember, because water, constant concentration, we're not looking at that. What we're looking at is the ions in the weak acid. If we increase the amount of the acetate ion, then we're bolstering up that conjugate base. So it'll be slightly more basic, but only slightly. But what happens if you add acid? let's say that we add some acid. Then you're going to shift the equilibrium to make more of your weak acid. So we're going to shift to make more acid, which means that you're going to have something that's slightly more acidic. And this is in comparison, again, to pure water, where the pH would be all over the place. If you add just a little drop of acid, you go from pH 7 to pH 4. And that's a big change. Here, if you're at pH 7 or so, you add a little bit of acid, maybe it's 6.9. Not a big change at all. So this picture up here just kind of demonstrates what happens when you add acid or base. It puts the images together that we were just working with. We can actually calculate the pH of a buffer. And the way that you do that is you can rearrange the Ka expression to find the concentration of hydronium. And that will give you the ratio of weak acid to conjugate base. This would be a good thing to remember, not just for acetic acid specifically, but how this is how this equation is formed, right? So you have hydronium. The hydronium concentration is equal to the Ka times the concentration of weak acid over the concentration of conjugate base. Doesn't matter which weak acid it is, it's always going to have this form if you want to rearrange and solve for the hydronium ion concentration. Once you have this concentration, then you can use that to calculate pH, because remember, the pH is equal to the negative log of the hydronium concentration. So let's do an example of this. The Ka for acetic acid is 1.8 times 10 to the minus 5, which is pretty small. What is the pH of a buffer prepared with 1 molar acetic acid and 1 molar acetate ion? And what we have is the equation for the dissociation of acetic acid. So I'm going to show you how to go from this equation to the Ka, from the Ka to solving for hydronium, and then we use that to calculate the pH. So I'll write those steps out. Step 1. We're going to write that Ka expression. Then we're going to rearrange the Ka expression to solve for hydronium. Then we're going to use the hydronium concentration to calculate pH. So let's get started. First, we're going to write that Ka. We don't care about the water. Concentration doesn't really change, so we're not going to include it. We always write the products on top and the reactants on the bottom. There's our expression. That's the first part. Let's color code it. Second part, we've got to solve for the hydronium concentration. So what I'm going to do for that is multiply by this bottom concentration here, on both sides. And that's going to give me the Ka times the concentration of the acid is equal to the concentration of the products. Still not finished isolating. So I'm going to divide by the acetate ion. And if you're wondering, yes, I am treating this exactly like, X and Y and Z like you would in any kind of a algebra expression. That's exactly what we're doing here. So now we've got the hydronium isolated. So if you were wondering how you got here, this is how. If you're not wondering and you just want to remember how it goes with the weak acid on top, and the conjugate base on the bottom, multiplied by the Ka, that's fine too. So we've rearranged all this. And now we need to put in some numbers and solve for the pH. The Ka was given in the problem, and it's 1.8 times 10 to the minus 5. The concentration of acetic acid is 1 molar. And we have 1 molar acetate ion as well. When you do that math, you should get 1.8 times 10 to the minus 5 molar. 1 over 1 is 1, right? Then you want to substitute that back into your equation for pH. But before we get there, I want to make sure to highlight where we got our information from. So that's the Ka. And here are the concentrations. Now we'll carry on. pH is equal to the negative log of the hydronium concentration so we put that in there. Don't forget that negative sign. Your calculator will tell you this answer. But remember, we need to take into account sig figs. The concentration that we have for our hydronium ion has 2 sig figs. So we need to have 2 decimal places. Your final answer should be 4.74 for the pH. Now, like I said, you don't have to go and, do the rearranging and stuff like I did to find this expression for the hydronium concentration. You can just remember how it's supposed to be arranged and write it out. So remember that the Ka is a constant at a given temperature. So we're usually assuming 25 degrees. Same thing with the Kw. Because it's a constant at a given temperature, the amount of hydronium is determined by the ratio of the weak acid and the conjugate base. When you add a little bit of acid or base, it only changes that ratio very slightly. So that means that your concentration overall of hydronium chain is going to be pretty small, and your pH is going to be pretty much the same. But if you add a large amount of acid or base, then you can exceed the buffering capacity of the system. So if you dump a bucket in there of acid, that might exceed the buffering capacity of your system. So there are limits to this. Buffers can be prepared from conjugate acid-base pairs, like we said, and here are some examples. So phosphoric acid, using conjugate base pairs from that, very, very popular in biological sciences. You can also have bicarbonate. You can have ammonium and ammonia. So the pH of the buffer solution depends on the conjugate acid-base pair that you choose. You choose the one that has the pH closest to what you're looking for. Phosphate buffers, very common when you're looking at biological specimens, when you're doing any kind of biochemistry or biology work. And you can look at the effect of using different ratios of your conjugate acid and your or your conjugate base and your weak acid on the hydronium ion. Here's the Ka of our weak acid. We've got the chemical equation here, the dissociation. Just like we've been writing, we don't include the water. And from there, we can write the acid dissociation expression. So I'm not going through that again, just reminding you how we would do that. So we get to this point, and then we can use that to rearrange and get the hydronium concentration. So that all has been done, and that's what we have here. Now we can play around with different ratios of weak acid and conjugate base. And that's what's in this table. These are the different concentrations of weak acid and conjugate base. The ratio is in the next column. So 10 to 1, 1 to 1, and then 1 to 10. So the very top one, we've got more weak acid. When you have more weak acid, you have a pH that is on the acidic side. When they're equal, it's neutral. And the bottom one, we've got more conjugate base, and you can see that it is basic. So just changing around the ratios of weak acid and conjugate base can change the pH of the buffer solution. To close out this chapter, we're going to talk about the link between buffers and blood plasma. So normally, your blood plasma has a pH of about 7.35 to 7.45. Very small, tight window. If changes occur to lower the pH below 6.8 or raise it above 8, your cells cannot function. So that is fatal. Carbon dioxide is continually produced because that's one of the products of cellular metabolism. We make our energy with the mitochondria. The mitochondria are putting out carbon dioxide. That's carried to your lungs and you breathe it out. But there's some of it that's actually dissolved in your body fluids, like your plasma and saliva. And that forms carbonic acid, which is a weak acid. When it dissociates, you make bicarbonate and hydronium. So stick that in the back of your mind. The carbon dioxide, all of it doesn't get eliminated through your lungs. Some of it is dissolved. In your kidneys, you're also supplying more of that bicarbonate anion. So remember, every good buffering system has a weak acid and a conjugate base. The kidney is supplying more of that conjugate base. So if you have excess hydronium ions entering your body fluids, they're going to react with that bicarbonate, which is the conjugate base. If you have hydroxide entering your body fluids, it will react with the carbonic acid. The ratio of weak acid to conjugate base needs to be about 1 to 10, and that maintains your normal pH of about 7.4. If you use these concentrations of weak acid and conjugate base, When you do the math, like we've been doing, where you rearrange your Ka equation to solve for the hydronium concentration, and then use that to calculate pH. You get a pH of 7.37, which is about 7.4. The concentration of carbonic acid is loosely associated with the partial pressure of carbon dioxide. So if the carbon dioxide level rises, then you're going to have an increase in carbonic acid. And you're going to shift to produce more hydronium, which lowers your pH. That's called acidosis. If you lower the carbon dioxide level, then you have a high blood pH, which is called alkalosis. This table has symptoms, causes, and treatments for acidosis and alkalosis. It is absolutely not something you want to mess with. Blood plasma pH is highly important, and when there are metabolic issues that change your pH, you can have some really serious medical issues, and it can actually lead to death. So buffering capacity and understanding how buffers work is very key to understanding how you yourself work. That's all that we're going to cover for Chapter 11. Thanks for watching, and make sure that you tune into the live lecture for practice problems and details regarding assignments and exams. Also, congratulations. This is the last Chem 104 lecture that you will need to listen to. So congratulations, you made it. Good job, you.